Ever wondered what light is? You can't touch it, you can see right through it. It's just there. It's probably some sort of wave, you might think, after remembering all those drawings you've seen of arrows coming out the sun. Wait, no, it has to be particles like everything else, right? Actually, it acts like both. It's a wavicle. This phenomenon can be explained using the principle of complementarity. In less than 5 minutes, hopefully you'll understand what this concept means. Okay, let's go back a bit. The complementarity principle was first announced in 1928 by Danish physicist Niels Bohr. As a leading scientist in the 20th century, Bohr's most important work was applying new quantum concepts to the atomic and molecular structure. His discovery, put simply, was that objects have different properties, but these properties cannot always be seen at the same time. Most of these properties existed in pairs that worked in a trade-off system, find one property and lose the other. This is perhaps one of the most important topics in quantum physics. One famous example is that of position and momentum. Originally proposed by German scientist Werner Heisenberg, the uncertainty principle states that the more precisely a particle's position is known, the less precisely the same particle's momentum and spin can be known, and vice versa. Imagine watching a car slowly coasting down a straight road. Well, now you can easily tell where it was and can reasonably assume it'll continue in the same direction. Now let's say the car was a particle. You would think you would do the same thing, right? Wrong. Suppose there's a baseball in the air. If you rapidly take pictures of the ball, you can tell its position by looking at a photo. But you can't tell from these photos how fast the ball is moving at that instant. Now suppose you took pictures of the ball a few seconds apart. The ball will appear blurred, but now you can estimate how fast the ball is traveling. However, you cannot tell where in that blur the ball is. Complementarity does not always involve a one or the other relation, however. In 1935, an influential thought experiment known as the Einstein-Podolsky-Rosen paradox arose. Einstein believed that some particles could move in such a way that it was possible to measure their position and momentum more accurately. This is where quantum entanglement comes in. The meaning of this is essentially in the term itself. Entanglement describes a phenomenon where two objects act on each other and become an entangled system. Imagine there is one child in the room and you know that the total age in the room is 15. Clearly, the child is 15 years old. Now what if I told you that there were two children in the room and that the total age was 15? Find the age of each child. The answer is impossible to find. There are many possibilities. Now place this concept into that of particles. Let's say we have a single hydrogen atom. From observing said atom, we can determine its position, spin, momentum, and energy, and other variables. Now imagine you have the same data except it's for two combined hydrogen atoms. It would be impossible to determine the properties of each individual atom in the pair. Hence, the data can only be described as a whole, no matter how far these particles are from each other. Another example of complementarity is that of waves and particles. Known as wave-particle duality, this principle states that when describing any elementary particle or any entity, you must describe it as both a wave and a particle. However, both states cannot be observed at once. This concept can be explained by the famous double-slit experiment originally designed by Thomas Young. First light, preferably laser light, is directed through two holes that are next to each other. When the light passes through it, it creates an interference pattern, direct evidence that it is a wave. However, when observed through a light-sensitive camera, one would see pinpoints, thus proving it's made of particles. Although scientists are uncertain of how this is possible, numerous experiments have proven this theory. In yet another famous experiment known as the photoelectric effect, Einstein showed that when photons at a high enough energy were hit against metal, they were able to push off electrons from the surface. He showed that photons can move in waves but at the same time travel in packets known as quanta. These principles fall under the Copenhagen interpretation of quantum physics. In summary, physical systems do not have definitive properties, and quantum mechanics can only provide probabilities. However, when these properties are actually measured, the number of probabilities collapse to 1 in an event known as a wave function collapse. In just this video, we learned the principle of complementarity, quantum entanglement, the relationship between momentum and position, wave-particle duality, and the basics of Copenhagen interpretation of quantum physics. Have fun exploring the amazing world of physics, and be sure to go out and confuse your friends.